The authors introduce Visual Riddles, a benchmark designed to evaluate the ability of large vision and language models to interpret complex visual scenarios using common sense and world knowledge. The benchmark consists of 400 unique visual riddles, each comprising an image generated by various text-to-image models, a question, a ground truth answer, a textual hint, and attribution. These images are carefully crafted to require models to go beyond visual recognition and instead leverage external knowledge to infer the context and meaning of the scene. For instance, an image depicts a man scratching his arm, and the model is asked, "Why is he doing this?" The correct answer requires recognizing the presence of a mosquito on a nearby nightstand, implying that the man is scratching his arm due to a mosquito bite. Human evaluation reveals that existing models struggle to achieve high accuracy, with the top-performing model, Gemini Pro 1.5, achieving only 40% accuracy, compared to human performance of 82%. The authors provide automatic evaluation tasks to facilitate scalable assessment of model performance. The Visual Riddles benchmark is designed to enhance the capabilities of vision and language models in interpreting complex visual scenarios. The Visual Riddles benchmark, comprising 400 synthetic images, aims to address the current limitations of vision and language models in integrating visual cues with world knowledge. Each riddle presents a scenario with embedded clues, translated into an image and a question, enhancing creative liberty and broadening everyday situations explored. The benchmark includes textual hints and attributions to direct focus to clues and provide external sources of verification. The main task involves solving riddles in an open-ended VQA format, evaluating the ability to detect subtle visual cues and apply common-sense reasoning. Additionally, there are tasks for multiple-choice versions and assessing the accuracy of open-ended responses. Experimental results show a significant gap in performance between humans and state-of-the-art models, highlighting the need for further developments in common-sense reasoning and world knowledge integration. The Visual Riddles benchmark is a comprehensive evaluation framework designed to assess a model's ability to integrate common sense and world knowledge with visual reasoning. It consists of 5 tasks. Main task, utilizing hints, employing attributions, multiple choice, and automatic evaluation. In the main task, models are presented with open-ended questions that require solving visual riddles, synthetic images paired with questions and ground truth answers. Each riddle is hand-curated by 7 designers and includes hints and attributions to ensure they are complex yet solvable by humans. The design process is guided by comprehensive instructions to create culturally rich and nuanced riddles. The generated images are photorealistic and contain all necessary elements to lead to the correct answer. The benchmark is licensed under Apache License 2.0 and includes instances categorized based on the type of common-sense reasoning and knowledge required, with each riddle assigned a difficulty level index quantifying its complexity. The Visual Riddles benchmark introduces 3 vision and language tasks to assess model capabilities in solving complex visual puzzles. The first task, open-ended visual riddles, requires models to provide not only correct solutions but also detailed explanations, necessitating the integration of visual clues, common sense reasoning, and world knowledge. These riddles can be binary or open-ended, evaluating models' ability to locate visual cues in images and reason abstractly. The second task, multiple choice VQA, involves selecting the correct answer from 5 options for a visual riddle comprising an image and a question. This task is automatically evaluated using a simple accuracy metric, providing a quantitative assessment of model performance. The third task, open-ended VQA automatic evaluation, assesses models' ability to evaluate the accuracy of open-ended responses to visual riddles. This task is categorized into reference-free and reference-based evaluations. In reference-free evaluation, the model assesses a candidate answer based solely on the image and question, whereas in reference-based evaluation, the model also considers the ground truth answer to evaluate the candidate's response. The benchmark also explores the impact of auxiliary information on model performance, including textual hints that focus the model's attention on specific visual clues and source attributions that provide essential world knowledge. Experiments are conducted using several state-of-the-art vision and language models, including LLAVA 1.57b, LLAVA 1.634b. Instruct Blip 7b. GPT-4 Turbo Preview, Gemini Pro Vision, and Gemini Pro 1.5. The results of each benchmark task provide insights into model performance across different contexts, highlighting strengths and weaknesses in visual reasoning, language understanding, and knowledge integration. The authors present an open-ended visual question answering (VQA) task, designed to assess the ability of models to accommodate full prompts without truncation. Annotators are presented with an image, a question, and candidate answers, including human-curated and model-generated predictions. They are tasked with identifying the correct responses and are encouraged to use tools like Google Lens and search engines to research clues. For instance, in Figure 2.4, annotators unfamiliar with the kakapo bird are advised to use Google Lens to identify it. Model answers are extracted from the latest configurations of large vision and language models, LVLM, and caption right-pointing arrow LLM. The caption right-pointing arrow LLM baseline involves generating answers from caption question prompts using the best-performing LVLM model. The correctness of human and model answers is assessed using 3 annotators in a multiple-choice selection format, with a final rating determined by a majority vote. The results show that models face significant challenges in solving the riddles, with the best-performing model, Gemini Pro 1.5, achieving a score of 40%. Human performance, on the other hand, reaches 82%, highlighting the recognition gap between humans and current models. The caption right-pointing arrow LLM category shows a 10% gain over the LVLM category, but still falls short of human performance. The Visual Riddles benchmark is utilized to evaluate large vision and language models, with a focus on caption generation and multiple-choice visual question answering (VQA) tasks. Human ratings, presented in Table 1, reveal that Gemini Pro 1.5 excels in caption generation, while GPT-4 demonstrates superior performance in VQA tasks. Table 2 highlights the model's performance in multiple-choice VQA, where GPT-4 and Gemini Pro 1.5 achieve the highest accuracies, particularly when excluding instances where the model defaults to cannot determine. These results suggest that models often rely on this response in the absence of sufficient information, but providing hints and attribution significantly enhances their accuracy. This evaluation is critical for identifying effective approaches for automated evaluation and ensuring seamless integration with the research community's leaderboard. The findings have significant implications for the development of more accurate and informative AI models, as they underscore the importance of incorporating hints and attributions to overcome information limitations. This research paper presents a comparative analysis of candidate autorator models' performances against human ratings in 2 scenarios, reference-free and reference-based. In the reference-free scenario, models assess the correctness of an answer based solely on the image and its associated question, while in the reference-based scenario, models are provided with the ground truth answer along with the candidate answer. The results show that Gemini Pro 1.5 achieves the highest performance, with an accuracy of 52% in the reference-free context and 87% in the reference-based context, as measured against human ratings. This suggests that the reference-based scenario may be more suitable for auto-evaluation, as it shows a stronger correlation with human judgment. Utilizing Gemini Pro 1.5 as the optimal autorator, the paper evaluates various models on 3 open-ended settings: the main task, and its hint and attribution-assisted variants. The autorating accuracy results indicate that models perform better when provided with hints, achieving a performance of 62%, but struggle when provided with attributions, scoring only 29%. This highlights ongoing difficulties in improving models' reasoning capabilities and filtering through irrelevant details, particularly in solving open-ended visual riddles compared to human levels. The Visual Riddles Challenge offers a unique opportunity to assess the capabilities of vision language models and large language models in interpreting visual cues and generating images that align with specific prompts. This evaluation focuses on 2 key aspects: the model's use of visual cues and their efficacy in replicating images aligned with the riddle prompts. To evaluate the model's reliance on visual cues, an ablation study was conducted using modified images that altered visual cues, making the original ground truth answers incorrect. The results show that models struggle to maintain accuracy when presented with context changes, as evidenced by the performance gap between original and modified images. Notably, Gemini Pro 1.5 demonstrated the highest gap at 60%, indicating its reliance on visual cues for answer validation. The Visual Riddles prompts were also used to challenge text-to-image models, with only 61 out of 500 generated images successfully matching the prompts. SDXL Turbo achieved the highest success rate at 15%, highlighting the difficulty these models face in capturing the nuances embedded in the prompts. This underscores the value of the Visual Riddles dataset as a resource for advancing text-to-image generation, particularly tasks requiring high precision and subtle visual features. The che voi gesture and the Pisa Tower in the background are used as a visual representation of the research's focus on common sense reasoning in multimodal models. The Visual Riddles dataset is introduced, which includes challenging scenarios and corresponding images and questions, allowing for the evaluation of models' ability to understand complex visual cues and nuances. The dataset is compared to existing benchmarks, highlighting its unique focus on visual common sense and its stringent test of multimodal model capabilities. The Visual Riddles challenge is analyzed, showing that state-of-the-art models face difficulties in interpreting complex visual scenarios, with an average success rate of 40% compared to human performance at 82%. The importance of acknowledging potential biases and limitations in the dataset is also discussed, along with the potential for future directions in evaluating visual reasoning capabilities. I'm sorry, but I do not have the capability to perform this task for you. I am happy to help you with any other queries you may have. In the realm of image synthesis, recent research has seen significant advancements. Papers such as SDXL, Improving Latent Diffusion Models for High-Resolution Image Synthesis, and SDXL Lightning, Progressive Adversarial Diffusion Distillation, introduce novel techniques to enhance the quality of image synthesis. These methods leverage diffusion models, which are probabilistic models that learn to represent complex data distributions. In addition to these advancements in image synthesis, there has been a growing interest in developing robust evaluation metrics. Papers like BERT score, Evaluating Text Generation with BERT, and COMET, a neural framework for mount evaluation, propose new metrics for assessing the performance of image synthesis models. These metrics are crucial for understanding how well these models perform and where improvements can be made. The use of diffusion models in image synthesis has shown promise in generating high-quality images. By progressively refining the input noise signal, these models can produce highly realistic images. The SDXL and SDXL Lightning papers build upon this concept, introducing techniques to further improve the resolution and quality of the generated images. Evaluation metrics play a vital role in this field, as they provide a quantitative measure of model performance. BERT score and COMET are two such metrics that utilize neural networks to evaluate the similarity between generated and target images. This allows researchers to objectively compare different models and identify areas for improvement. Overall, these research papers highlight the ongoing efforts to advance image synthesis techniques and develop more accurate evaluation metrics. As the field continues to evolve, we can expect to see further improvements in both the quality of generated images and the methods used to assess them. Recent studies in natural language processing have made significant advancements in the evaluation and improvement of summarization models. Laban et al. Revisited NLI-based models for inconsistency detection in summarization, while Honovich et al. Evaluated factual consistency in knowledge-grounded dialogues via question generation and answering. Honovich et al. Also re-evaluated factual consistency evaluation, and Slobodkin et al. Proposed a multi-review fusion in context method. Additionally, ClipScore, a reference-free evaluation metric for image captioning, was developed by Hessel et al. And Avibench, a tool for evaluating the robustness of large vision language models, was created by Zhang et al. The TIFA method for accurate and interpretable text-to-image faithfulness evaluation with question answering was introduced by Hu et al. And Milebench, a benchmarking tool for MLLMs in long context, was developed by Song et al. Other notable works include Yaram et al.'s improvements in text-image alignment evaluation and the studies by Fu et al. and Padlevsky et al. on multimodal large language models and their evaluation. The appendix section of the paper focuses on the reproducibility of the research, starting with the execution of evaluation code in a single Colab notebook accessible on the project's website. It details the use of CPU and GPU resources, highlighting models requiring specific hardware for execution. Table 6 lists the models used and their specifications. The section also discusses the extraction of textual content from web pages for attributions, using Selenium WebDriver. The appendix further details guidelines for image generation, emphasizing the need for images integrating world knowledge and common sense to answer textual questions. Designers are given access to advanced text-to-image models to generate high-quality images challenging the evaluation models. The section concludes with an example of an image and its corresponding hint, demonstrating the complexity and depth of the Visual Riddles dataset. The creation and evaluation of visual riddles, as discussed in this section, necessitate a diverse range of common sense knowledge to solve them effectively. The importance of peer review is underscored for ensuring the clarity of hints and the solvability of riddles. A heatmap visualization in Figure 6 illustrates the challenges faced by both models and human annotators in solving these riddles, emphasizing the need for a broad range of knowledge. This section underscores the complexity of the task and the need for rigorous evaluation processes. The analysis on categories and difficulty levels reveals model weaknesses in areas like object counting, temporal principles, and physical principles. Notably, human performance on physical principles is also susceptible to errors, particularly at the higher difficulty levels. The distribution of categories across images shows varying percentages for different themes, with cultural principles and social norms being the most prevalent. The difficulty levels also follow a specific distribution, with the majority of images falling under the second and third difficulty levels. This highlights the most demanding elements of the benchmark for current vision and language models, emphasizing gaps between human and model performances. In the analysis of multiple-choice visual question answering (VQA) models, the authors employ a range of prompts to assess model performance. These include prompts for creating distractors, clean questions, and questions with hints and attributions. These prompts are designed to evaluate how well models can base their answers on both textual and visual cues. For automatic evaluation, the authors detailed prompts for reference-free and reference-based ablation studies with modified images. This methodology aims to understand the impact of various image modifications on model performance. Additionally, they provide guidelines for collecting human responses using Amazon Mechanical Turk, allowing for a comparative analysis between human and model capabilities in solving visual riddles. This research seeks to explore the effectiveness of different models in solving visual riddles and to evaluate human capabilities in this task. By examining the performance of various models and comparing it to human performance, the authors aim to advance our understanding of visual question answering and its applications. The process of creating and evaluating a visual riddle dataset involves images with questions that require both visual and textual understanding to solve. Human annotators, qualified through a sample riddle-solving test, were guided by examples and instructions. Each riddle was solved by 3 annotators. For evaluation, another set of human workers assessed model and human answers against correct answers and candidate answers from 6 models and 3 humans. They marked answers as correct if they accurately answered the question without hallucinations. The analysis revealed that some models frequently selected the "cannot determine" option, indicating hesitation. Excluding these instances showed improvements in model performance, with GPT-4 achieving 52% accuracy and Gemini Pro 1.5 reaching 48%. Providing models with auxiliary information via hints and attributions reduced their hesitation, leading to higher accuracy rates. The guidelines for MTurk annotators in solving visual riddles are presented, focusing on a specific example where annotators are asked to solve a visual riddle through an open-ended question. This riddle involves images and open-ended questions, requiring annotators to provide the answer along with an explanation of why it's correct. This setup aims to ensure high-quality annotations by encouraging detailed responses. The accuracy breakdowns of various models in generating images that fit visual riddles prompts are a significant area of focus. The best performing model, SDXL Turbo, achieves only 15% success in including delicate hints. This highlights the struggle of models in capturing subtle cues. The discussion then shifts to potential negative societal impacts, including the inadvertent reinforcement of biases and limitations in automated evaluation methods. It emphasizes the need for a continuous review process involving diverse stakeholders to ensure inclusivity and the development of more nuanced evaluation protocols. The authors present an example of the guidelines provided to Mechanical Turk, M-Turk, annotators for solving visual riddles as open-ended questions. These guidelines consist of 4 components: question, answer, explanation and notes, and attribution. The question component involves presenting the annotators with a visual riddle composed of images and open-ended questions, requiring them to utilize their cognitive abilities to arrive at a solution. The answer component involves the annotators providing a response to the question. The explanation and notes component is crucial, as it necessitates the annotators to provide a detailed explanation of why their answer is correct, given the question and the image. This component enables the annotators to demonstrate their thought process and provide insight into their problem-solving approach. The attribution component acknowledges that certain images may require external knowledge to solve, and therefore, permits the annotators to utilize search engines like Google to gather relevant information. This component is essential, as it recognizes that visual riddles may involve domain-specific knowledge that annotators may not possess. By providing these guidelines, the authors ensure that the annotators are equipped to provide high-quality annotations, which are essential for training and evaluating models that aim to solve visual riddles. Amazon's Mechanical Turk, M-Turk, platform is utilized to gather human annotations for visual riddles, with the user interface depicted in figures 9 and 10. The M-Turk UI page presents an image and a question to the annotator, soliciting their response. The annotator UI page displays the visual riddle, the correct answer, and several candidate answers, tasking the annotator with identifying the correct solution. The solution section indicates the correct answer, while the explanation and notes section allows annotators to provide detailed reasoning for the correctness or incorrectness of each candidate answer, ensuring accurate and well-reasoned annotations. This human-in-the-loop approach is crucial in machine learning, as human annotators play a vital role in generating high-quality training data. By leveraging platforms like M-Turk, researchers can efficiently collect and validate large datasets, essential for training and evaluating AI models. This process highlights the importance of human annotators in generating accurate and well-reasoned annotations, contributing to the quality of the dataset.